Our universe. It's awe-inspiring and baffling. From colossal explosions of stars to the strange movements of tiny particles. Each new discovery seems to reveal another layer of mystery. Our understanding of the world around us has taken us from the Stone Age to the Silicon Age. Now, ironclad laws of physics are breaking apart. What we believe is reality may not be real at all. The future of humanity depends on our discovering how the universe really works. Space, time, life itself. The secrets of the cosmos lie through the wormhole.
Think of existence as an enormous web that we're all woven into, but we can't see the whole thing. We just see the patch where we are standing. We can't see the whole of reality. But what if we could see it all? What if we could understand how the whole of creation joins together? The rewards of finding this equation would be enormous. A revolution in science far beyond anything that has come before. A great leap forward that will transform life on Earth and ensure our survival as a species. But what hope do we mere mortals have of uncovering the hidden secrets of the universe, of knowing the mind of God?
I remember my first day of school, the day I was supposed to start learning about the world and how it works. I made it about 20 yards to the schoolhouse, then I froze. What hope did I have of understanding everything, or anything? My mind reeled. I ran back home. I wonder if scientists feel much the same way. There is so much we don't know about why the universe functions the way it does. Imagine trying to play a game of chess if you don't know the rules. You might figure out some moves, but a lot of it would make no sense. Once you know the rules, though, you can begin to move the pieces with purpose. Science is our means to discover those rules, and so far we've revealed quite a few of them. But what if we've got them wrong? Deep in the basement tunnels of Purdue University, scientists Jerry Jenkins and Ephraim Fishbach have discovered that one of the supposedly unbreakable laws of physics is broken. It began with a mystery.
I'll come out and set up a few tethers and receive some tools, and then he'll come out right after me.
The second week of December of 2006, astronauts from the space shuttle were up at the International Space Station, and everybody was out on an EVA. And there was a solar storm. Because the astronauts were all out there, the solar storm was big news. Sitting there and watching that news story, I thought, well, wouldn't that be funny if I saw that appear in the data?
Jenkins studies a powerful source of energy we can't see, but is all around us: radioactivity. Every second of every day, the sun sprays out showers of radioactive atoms. These atoms are unstable. They spit out energy until they burn away in a process known as radioactive decay. Radioactive decay is supposed to be a random process that cannot be affected by anything.
In early December of 2006, we're plotting this. It's a nice straight line. It's following exactly like it should. But then on December 13th, the flare happened, and we see that the decay has actually departed what the standard decay line should have been. And it departed it for quite some time. This is actually the space of about 4 days. It appeared, or so it seemed, that something may have been changing this radioactive decay process, which nothing is supposed to change.
Fischbach, a theoretical physicist, struggled with the huge implications of this finding. Knowing how fast radioactive particles break down is critical for nuclear power, weapons, electronics, and medicine. Could it be that a concept so uniformly accepted and central to modern life was wrong?
The idea that nuclear decays cannot be influenced by an external influence is so fundamental to so many aspects of quantum physics, nuclear physics, elementary particle physics, that changing that would likely have a significant change on our understanding of the universe as well as on practical applications.
Still reeling from this shock, Jenkins and Fischbach uncovered another mystery. Radioactive decay was not just being affected by the solar flare. The discharge of radioactive particles appears to change depending on how close the Earth is to the Sun.
When the Earth is closer to the Sun, around January 4th, the rate of radioactive decay seems to be faster, and we're farther away, the rate seems to be smaller. Now, we're going to illustrate this in the following way. I represent the Sun, and Jerry is going to represent the Earth, and the bucket represents a sample of radioactive radium atoms. And you'll see that as Jerry moves in ellipse, where he's closer to the Earth around January 4th, more tennis balls are thrown out, meaning more particles come out than happen around July 4th.
This small change in numbers could have big consequences. Cancer patients receive very tiny doses of radiation to kill their rebel cells. If the strength of that radiation changes seasonally, they might get too little or too much of a dose. Knowing the difference could save lives. But the duo's most important discovery could secure the future of the human race.
40 hours prior to the actual time of the flare, we saw the decay rate change and actually leave the line. After the flare, it started to recover and move back toward the line. So this possibly gives us the opportunity then to predict when these solar flares are happening.
A large solar flare could wipe out every one of the nearly 3,000 satellites orbiting the Earth. In a flash, we would lose the internet, GPS, television, radio, telephones, and the systems that control our power grids. Knowing a flare is coming could avert a global apocalypse.
If this phenomenon is real, as we believe it is, then it's essential to understand how this is happening, because this will certainly be a part of a bigger puzzle that we must understand to put all this physics together.
We're groping in the dark of the vast universe, thinking we have uncovered its deepest truths, then finding we still have much to learn about the rules of nature. And nature does not make things easy for us. Down at the smallest scale of existence, deep in the weird world of quantum mechanics, it seems to play by two different rules at the same time. And the deeper we probe into its mysteries, the more we are forced to ask not just how the universe works, but whether anything is real.
Quantum mechanics has transformed the world. We owe most of our amazing technology to its explanations of how extremely small particles behave. But we don't really understand it. In the quantum world, nothing seems to make sense. Reality stops being real. This mystery is our greatest obstacle to unlocking the secrets of the universe. If we can solve it, we may hold the keys to creation itself.
Vienna, Austria is arguably the birthplace of quantum mechanics. This is where you will find the leading quantum experimentalist in the world, Professor Anton Zeilinger.
When I first heard of quantum mechanics, when I was a student, I was immediately struck by three things. First, its unbelievable mathematical beauty. Secondly, by the incredible precision to which the predictions work. And thirdly, by the fact that it doesn't make sense.
Quantum mechanics describes the behavior of all the tiny particles that everything is made of. This knowledge has given us computers, nuclear power, satellites, advanced medicine, most of the great leaps forward humanity has taken in the past 100 years. But the quantum world seems to run contrary to everything we know about the laws of nature. Simply put, down where things are very, very small, the universe follows a different set of rules. Consider the phenomenon of quantum non-locality. When two tiny particles instantly share information across vast distances.
If there were quantum dice, it would mean that if I throw one die here, it shows a certain number. The other die thrown at some distant location would show the same number. How can that be? Quantum mechanics describes it very well.
Time and again, Zeilinger has proven that no matter how extreme its predictions, quantum theory works, even though it shouldn't. And perhaps the ultimate proof of just how unsettling quantum mechanics can be is something called the double-slit experiment. It will make you question whether reality exists at all. This simple configuration shoots particles of light called photons, one at a time, through two tiny slits in a screen.
We have a laser which produces light. This light is attenuated such that only one photon at a time emerges. This photon passes through a two-slit assembly, and then we have a camera which registers the pattern behind the two-slit assembly. So what we see is that the photons arrive one by one on the screen, some here, some there, and it looks pretty random.
Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of two stripes on the wall. And you would be wrong. They mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the two slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in two places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors, and the wave pattern comes back. This suggests that we can change the way reality behaves just by looking at it. Does this mean that reality itself is not real?
The modern answer is that the path taken by the photon is not an element of reality. We are not allowed to talk about the photon passing through this or this slit. Neither are we allowed to say that the photons pass through both slits. All this kind of language is not applicable.
So, do we just keep reaping the benefits from quantum mechanics and accept that deep down, nature plays by a set of rules that will forever remain a mystery?
The interesting message here is that we have quantum physics now around for nearly 100 years. and we are still working at the foundations. And that tells me that when we found it, it will be an absolute revelation. It will be something different from what we have been thinking.
If the quantum theorists are correct, we will never understand the fundamental level of the universe. Our hopes of finding an ultimate theory will fail, and the human race will hit a roadblock it can't break through. But what if they're wrong? What if the truth about what happens deep inside you, me, and everything else in the universe is there, if we're willing to look for it? For most of the 20th century, scientists believed quantum physics could not be explained, that we would just have to accept that we'll never know why things behave as they do down at the deepest levels of existence. But now, a growing band of rebel scientists thinks there may be a logical explanation for quantum weirdness after all, and new hope for revealing the ultimate truth of our universe.
The trail begins here, with a drop of silicon. In his Paris laboratory, physicist Yves Coudet and his team conduct an amazing series of experiments. They are observing the behavior of silicon droplets bouncing in lockstep on a vibrating plate.
The liquid of the drop never touches the liquid of the substrate, so they're always separated by air film. And in fact, this is stable. You can keep the drop bouncing on the liquid surface for several days if you wish.
Using a camera that shoots 1,000 frames per second, Coudet has discovered that these droplets mimic behavior seen in the quantum world. And that shouldn't be possible, because the quantum world and the large-scale world play by two different sets of rules. Yet here we see a single droplet moving randomly like a quantum particle, but behaving like a quantum wave. If you watch this carefully, you'll notice that the wave appears to be guiding the droplet. In fact, the wave fields around the droplets develop a memory of the trails they have followed. Despite their random behavior, they follow a small number of paths. Again, this is eerily similar to the behavior of quantum objects. This runs so contrary to popular belief that at first, Coudet refused to believe what he was seeing.
In any physics experiments, you only see what you are prepared to see. Of course, this was very obvious that there was a memory, but it took us some time to realize that it was that we were observing, because you have to adapt to this new idea.
Perhaps most revealing of all, Coudet has reproduced the double-slit experiment using his bouncing silicon droplets. The mystery of quantum mechanics is, how can things like electrons sometimes behave like particles and sometimes behave like waves? Perhaps this is the answer. They are particles and waves. Of course, this system, though small, is not quantum.
Our system is not a model of quantum mechanics, but it is an association of a particle and a wave, and some of its properties are similar to the properties that are observed in quantum mechanics.
Coudet won't claim that his experiments show us what is really happening down at the deepest layers of existence. But this man will. To him, those droplets are more proof that the quantum world makes sense after all, and that reality really exists. Anthony Valentini of Clemson University is a quantum heretic. He loudly proclaims that physics went off the rails in the 1920s when it embraced the doctrine of quantum uncertainty, which says that nothing is real until we look at it. Valentini champions the theory that got left behind. It was created by one of the pillars of early 20th century physics, Louis de Broglie.
Louis de Broglie's original idea is that an electron is both a wave and a particle all the time. It's not the case that, well, sometimes it's a particle, sometimes it's a wave. There is a wave guiding a particle at all times. And de Broglie called this a pilot wave.
In quantum theory, there is something called the probability wave, a purely mathematical object that tells you the chance of finding an electron at any point in space. Pilot wave theory treats this wave as a real physical object.
So a simple analog is a bottle. Someone is on an island and they want to send a message, so they write something on a piece of paper, put it in a bottle, close it, and throw it in the ocean. And water waves simply push the bottle along.
There is a crucial difference between the waves we know and the pilot wave. According to the theory, pilot waves exist in hidden dimensions of space beyond the three we know. If true, this means that contrary to the accepted theory in physics, quantum objects obey the same rules as large objects. They do not exist in two places at once. They are part of the real world.
I think that quantum mechanics itself is not even a candidate for the truth about the microscopic world, because it simply doesn't attempt to describe precisely what the microscopic world is. And the mere fact that there are different theories about what the answer might be doesn't mean that there's no answer. And eventually one of them is found to be the correct one.
To understand how the universe works, we need to unlock why the quantum world is so different from the world we know. It is an unsolved mystery that affects every single person on Earth. And this man thinks he can solve it.
The more we understand the inner workings of the universe, the more we humans are rewarded with new medicines, new technologies, and undreamed of improvements in our lives. But some say we're a long way off from unlocking the universe's deepest secrets. We want definitive answers. What we have are mysteries upon mysteries.
And one of the greatest mysteries is how the big stuff and the small stuff in the universe fit together. Two well-tested theories describe how matter behaves: relativity theory, which governs the physics of the large, and quantum theory, which describes the very small. If there were a couple, relativity would be a logical, pocket protector-wearing engineer who strictly follows the speed limit of light. Quantum theory would be his volatile artist wife who seems to be everywhere at once. On paper, they don't get along. But in the real world, they are a happy pair. And like some real-life odd couples, no one understands why. The mystery boils down to gravity. Gravity dominates the world we know, and thanks to Newton and Einstein, we understand it pretty well. But physicists have no idea what role gravity plays in the quantum realm, or its effect on space and time. If we crack this mystery, we will finally know if it is possible to travel back in time, or through a wormhole. Petroshava has a history of exploring the wild frontier of physics. Now he's tackling quantum gravity.
So how do you reconcile quantum mechanics and gravity? There are several different ways it can happen. Either quantum mechanics is stronger and wins, and gravity has to be modified, or quantum mechanics has to be modified and gravity stays the same as in Einstein's general relativity.
Petter feels the key is to watch how things change in scale between the upper layers of nature, where gravity holds sway, and the quantum layers down below.
Nature organizes itself in layers of structure, and you see more and more layers as you zoom in and gain a better resolution of how you view the system. It's one of the most important theoretical concepts in modern physics.
To Petter, nature is an archaeological dig that we're slowly excavating layer by layer. Right now, we're only capable of uncovering a small part of the vast and complex ultimate truth. But we can learn a lot by comparing the layers we can see.
In this picture, the two images of Mona Lisa represent the two faces of space-time, space and time. They look the same when we look at it at large scales, but perhaps when we zoom in and look at the system at much smaller scales, it could be that space and time scale in a very different way. This could be the missing piece of the puzzle of quantum gravity.
Petter suspects that as you shrink down to the smallest and deepest level of existence, space begins to stretch at a different rate from time, until they tear apart.
Think of space-time as analogous to this sheet of paper. At macroscopic scales, it's smooth and geometric, two-dimensional. But if you tear the piece of paper into two halves and look at the edge of the paper, zoom in, zoom out, the structure is similar to itself, but only if you stretch in the horizontal direction with a different rate than when you stretch with the vertical direction.
From a distance, the tear looks smooth, but close up, you can see mountains and valleys along the edge. Similarly, space and time seem perfectly joined from a distance, but close up, you can see the separation. Petter thinks this tearing apart of time and space at the microscopic scale is precisely why the strange rules of quantum mechanics emerge. If space and time are unhinged, particles can't be in a specific place at a specific time. Hence, fuzziness and uncertainty. Unraveling the enigma of quantum gravity is a major hurdle in our quest to understand how the universe works. But it shrinks against the magnitude of the biggest mystery facing humanity. 95% of the universe is missing. This woman may know where and what it is.
The more we peel away the layers of nature, the more we realize that something is missing, something big. An enormous chunk of the universe seems to be invisible. We can't see it, hear it, or detect it in any way. But if we want to unlock the secrets of the universe, if we want to advance as a species, we have to find out what and where it is.
The universe began with the Big Bang, a shattering explosion of raw energy. That energy burst outward in a mass of superheated plasma. As it cooled, it began to clump together into all the material in the universe, the solids, liquids, and gases that everything is made of. To crack the cosmic code that underlies our universe, we have to understand energy in all its forms. But what if almost 95% of the universe is made of a form of energy we can't see and don't understand? These are the kinds of questions confronted daily in Geneva, Switzerland, the home of the world's largest particle accelerator, the Large Hadron Collider, and also hundreds of physicists. Claire Burridge is one of them, but she's hardly typical. Young, female, and an accomplished figure skater, Claire is trying to solve the vast mystery of the missing universe.
if we think about the sun, the light from the sun carries energy to us here on Earth, and we can feel the warmth of the sun on our skin on a nice day. But Einstein tells us that what's happening is that energy and mass are the same thing. So in the center of the sun, mass is being turned into energy, and that's what's transmitted by the light here to us on Earth. So the energy from the sun we know and we understand very well, but it seems like there's another form of energy out there in the universe called dark energy that we don't understand at all.
Accepted laws of physics dictate that the expansion of the universe after the Big Bang should be slowing down. But recent astronomical observations have revealed that the expansion is rapidly speeding up. Some unexplained form of energy is pushing galaxies apart.
So at the moment I'm moving forwards even though I'm not doing anything because of the force of gravity. But if I were in space where there are no forces acting on me, I shouldn't be moving at all. If I'm moving forwards, then there has to be something very strange acting on me, and this is what we call dark energy.
How much of the universe is dark energy? Put it this way. Here's the universe. This sliver, 4.6%, is all the matter we can see. Near massless particles called neutrinos take up another 0.4%. We think that something called dark matter accounts for another 23%. Dark energy is the remaining 72% of the mass and energy of the universe. We cannot see it, touch it, taste it, or detect it, but cosmologists are certain it is there. Without dark energy, gravity would cause the universe to collapse in on itself. Claire suspects that dark energy is a byproduct of a radical new piece of physics, an undiscovered particle called the chameleon. These mysterious particles actually carry an entirely different basic force than the four that physicists know about, a fifth fundamental force.
In physics as we understand it, there are four forces. So they are gravity, which holds us here on Earth. There are the electric interactions between atoms, and the strong and weak forces that control what happens in atoms. And so if there is something new, a new particle like the chameleon, like dark energy, it's going to look to us like there's a fifth force out there.
This force carrier is called the chameleon because it can change its appearance. When it is heavy, it becomes sluggish and ineffective. When it is light, it can zip around much faster and become stronger. How heavy it is depends on its environment, how much stuff is around it.
So here on Earth, there's a lot of stuff around, a lot of matter, and the chameleon becomes very heavy, very massive. It doesn't interact with the things around it very much, and that's why we don't see it in our everyday lives and in experiments here on Earth. But in intergalactic space, where there's almost nothing, the chameleon becomes very, very light, and it can interact with things over huge distances. And that's why it can drive the acceleration of the expansion of the universe.
This shape-shifting property explains why the chameleon has yet to be spotted in our particle accelerators. It should be everywhere, inside you and me and far out in the cosmos. But how do we detect a master of disguise?
The chameleon shows up in experiments on really tiny scales and on really huge scales. So you can look for it in the ways that particles behave in colliders on really tiny scales, but also it affects the way that light travels. And so we can look on very large scales at how light from stars comes to us and whether we can see the effects of the chameleon there.
Our slow and steady understanding of electromagnetism and the nuclear forces has transformed our lives. From electricity to telecommunications, transportation to warfare. What benefits could dark energy bring us?
very hard to say now how a better understanding of dark energy is going to make people's lives better, but in the past, understanding things better has always led to benefits for mankind. So in some ways, understanding dark energy, for understanding the universe, it's more important than understanding the physics that we know here on Earth. The particles that we understand make up about 1% of the universe as we know it. Dark energy is a massively more important contribution.
Dark energy is the unknown variable in our quest to crack the cosmic code, to find a set of equations that describe how the universe really works. But this man says that doesn't go far enough. He believes equations don't just describe the universe, equations are the universe. And we are all living inside them.
We are hunting for an ultimate equation, the theory of everything that will explain the mechanisms of the universe and revolutionize life on Earth. One man believes that equation exists, and the solution is the universe. According to him, the equation of everything is everywhere you look, and we are all part of it.
Max Tegmark lives in Winchester, Massachusetts, a northern suburb of Boston. He's an outdoorsy sort who likes to go on long walks and think. But Tegmark's thoughts are a bit more exotic than your average power walker's ponderings.
I think the reason our universe is so well described by math is that it is math, in the sense that we are living in a giant mathematical structure. So the reason we physicists have discovered all of these equations which describe our world so well is simply because these equations can approximately describe the true math, which is our reality.
To Tegmark, equations are windows on the universe, and the universe is pure math.
At first glance, our universe doesn't seem mathematical at all. We don't have big numbers written visibly in the sky. But if we look more closely, we find mathematical patterns and shapes all around us. Like if I mess around with my garden hose here, the water makes this very simple shape called a parabola, which has this extremely simple mathematical equation, y equals x squared. This mathematical shape, the parabola, is really built into nature at quite a fundamental level because it describes the motion with gravity of any object, regardless of what it's made of. When we look around us in the universe, we see shapes everywhere. We see that all the planets are going around the sun in a shape called an ellipse, which looks like a stretched circle. And anything orbiting anything out there in the universe, why is it always that shape? You know, not a figure 8 or a square. As soon as we scratch beneath the surface, we start to discover all these patterns and regularities and even numbers. Like if I just pick up some sticks here and I ask, like, how many sticks can I put here which are perpendicular to each other? I get a number, I get 3. We have a fancy number for this in physics. We call it the dimensionality of space. And these numbers that are built into nature are very important because if you tweak them a little bit, if you say the proton isn't 1,836 times heavier than an electron, but 5,000 times heavier, for instance, we would die. In fact, if you change many of the numbers by just a few percent, the sun might blow up, or suddenly atoms would collapse, and life as we know it just wouldn't be possible. So not only are these numbers there, but they're extremely important for just understanding the very essence of our reality.
This brings us back to an uncomfortable notion suggested by the prevailing theory of quantum mechanics. At the deepest level of reality, nothing is solid. There is only information. Numbers adhering to a set of rules we don't yet understand.
The only properties an electron has is a bunch of numbers. We physicists have names for them like spin and charge, but they're just numbers. There's really nothing there at the bottom level except numbers, except math.
Math may be the ultimate truth, but given our limitations and how vast and strange so much of nature seems to be, is it even possible to solve this problem? Can we ever know how the universe really works?
There's certainly no guarantee that we'll find the ultimate equation, but I think we do have a shot at it. It's really remarkable how far we've come as a species in the last 100 years, beyond our wildest dreams in understanding stuff. And there's no better way to guarantee we're going to fail than to not try. If I'm wrong and there's something inherently non-mathematical about the universe, then physics is ultimately doomed. We're going to reach a roadblock beyond which we just can't proceed. Whereas if I'm right, that would actually be a very happy situation where there is no roadblock and our progress would only be limited by our own imagination.
Will we ever see the entire web of reality? Can we find and will we understand the ultimate truth? Right now, we're like archaeologists who have uncovered a small triangle buried in the sand, the tip of an enormous pyramid that we can't yet see. Perhaps it's presumptuous for human beings to think we ever will, but we continue to uncover the truth bit by bit, piece by piece. If we keep digging, we may finally reveal the full beauty of creation and perhaps steal a glimpse into the mind of God.